This works now is we can have an x which is say like 2.0, 3.0 dimensional, because these are two numbers, and then we can feed those two numbers into that neuron to get an output. And so when you use this notation, n of x, Python will use call. So currently call just returns 0.0. Now we'd like to actually do the forward pass of this neuron instead. So what we're going to do here first is we need to basically multiply all of the elements of w with all of the elements of x pairwise. We need to multiply them. So the first thing we're going to do is we're going to zip up delta w and x. And
I guess it takes in a vector value to input directly. Whereas input is not just one number necessarily. That's what n in is, the number of inputs, or rather the dimension of the input. Yeah, and then there with his weight matrix, he constructs something of length n in. And since the bias is just a number that's added after the fact, it's a single scalar. Yeah. Have you seen the zip function already? Okay, it's a very useful function. Here's what it does.
In Python,
Maybe he'll
zip takes two iterators, and it creates a new iterator that iterates over the tuples of their corresponding entries. So, for example, just to show you, we can print this list and still return 0.0 here.
Get it? You forgot the friends on print on this.
Sorry. I'm in my... So we see that these w's are paired up with the x's. W with x.
Yeah, the two lists get dipped into a list of tuples. Yeah.
For wi xi in, we want to multiply wi times xi.
Yeah, it's a sum of a zip of products, and yeah, that works just fine. Oh yeah, zip will also, when the things being iterated over have different lengths, it'll just truncate to the shortest one by default. There's some argument where it can instead pass an error, which is annoying. Or you can try to assert they're supposed to have the same length. This sometimes comes up.
And then we want to sum all of that together to come up with an activation, and add also delta-b on top. So that's the raw activation. And then, of course, we need to pass that through a nonlinearity. So what we're going to be returning is act.10h. And here's out. So now we see that we are getting some outputs. And we get a different output from a neuron each time because we are initializing different weights and biases. And then to be a bit more efficient here, actually, sum, by the way, takes a second optional parameter, which is the start. And by default, the start is 0, so these elements of this sum will be added on top of 0 to begin with, but actually we can just start with delta-b, and then we just have an expression like this.
Actually, optimizations of that kind are exactly the sort of optimizations that compilers are pretty good at coming up with, so that people don't have to employ all these little bits of cleverness. The problem with all this cleverness is that over time, why someone did something this way precisely is just like forgotten, often by them first, and then no one knows, and it hinders the future evolution of a system because it gets more and more complicated.
And then the generator expression here must be parenthesized in Python. There we go. Yep, so now we can forward a single neuron. Next up, we're going to define a layer of neurons. So here we have a schematic for a...
All right, write in the code for the neuron class first, then we'll define the layer. In fact, we can try defining the layer ourselves. The way he defined it, a neuron is like a function from n to 1, and so the layer is going to have concatenate multiple of these n to 1s to get something that's n to M, whatever the output dimension is supposed to be. And a layer will just be like, it will probably have a definition very similar to neurons, something like instead of a list of values, a list of neurons, and then the bias would be a list of biases. To sort of like vectorize one step up or one rank up. Let's try writing it. But first define neuron. I certainly have to.
Mechanistic, which sounds like a mechanistic understanding. So this is actually I think actually having these equations for T and O makes sense. At least for T. I don't know, I'm starting to believe more and more that there's like an actual story in the particulars of this T to the end.
Yeah.
You can disagree. Well, you always see the scaling thing.
Yeah, no, I think there is. I just like kind of. I just wonder if this story specific to the Met3 or this is like in general. Because like again, you don't need those arrows to be symmetric, and I think this is what the Met3 is doing.
Yeah, it has to be symmetric. Yeah. So you know, there's another let me show you a case where you still get a fractal, but it's not symmetric. And,
yeah, what about the case when it's not fractal at all? Just like something.
I think that's fine. It is important to note that in general, we actually do expect fractals.
Okay.
Or at least I should say there is reason to expect fractals. And the reason is basically the fractal. You see where the fractal's coming from. It sounds like you understand it more than anyone. And like it's just kind of this reapplication of these things, which is it sounds quite good.
Hang on, I'm getting the weird syntax there.
Yeah, I should maybe just. Yeah, I don't know.
Actually, I'm going to copy and paste one of the.
Okay, just tell me, is this a fractal?
Yes.
Yeah.
Oh, that's why I put it. We just use the built-in name.
So like this thing. These two, for instance, the two examples.
Yeah.
Where if this thing is going on, I would expect you exactly get this kind of asymmetry because these things are not.
Yeah.
Okay. Things that are missing. This. So quantification.
I have two of them. This one's still simple.
MLP. So we see that these MLPs, each layer, this is one layer, has actually a number of neurons, and they're not connected to each other, but all of them are fully connected to the input. So what is a layer of neurons? It's just a set of neurons evaluated independently. So in the interest of time, I'm going to do something fairly straightforward here. It's literally a layer is just a list of neurons. And then how many neurons do we have? We take that as an input argument here. How many neurons do you want in your layer? Number of outputs in this layer. And so we just initialize completely independent neurons with this given dimensionality. And when we call on it, we just independently evaluate them. So now instead of a neuron, we can make a layer of neurons. They are two-dimensional neurons, and let's have 3 of them. And now we see that we have 3 independent evaluations of 3 different neurons, right? Okay, and finally, let's complete this picture and define an entire multi-layer perceptron, or MLP. And as we can see here, in an MLP, these layers just feed into each other sequentially. So let's come here, and I'm just going to copy the code here in the interest of time. So an MLP is very similar. We're taking the number of inputs as before, but now instead of taking a single N-out, which is the number of neurons in a single layer, we're going to take a list of N-outs, and this list defines the sizes of all the layers that we want in our MLP. So here we just put them all together and then iterate over consecutive pairs of these sizes and create layer objects for them. And then in the call function, we are just calling them sequentially. So that's an MLP really. And let's actually re-implement this picture. So we want 3.
Okay, did that make sense?
Yeah.
In that case, open up the video on yours and share your screen. Make sure to share the sound too.
Possibly.
And then I can see screen and also like your code. That might be easier.
Yeah, so I mean, one very interesting story is that you have a way to predict the structure of the attention heads in a model agnostic way in Tetra patterns. Which sounds very cool to me. And what's more is you have that's just like one aspect of it. You have this whole story for exactly this. So and there's also this aspect of it that is, I guess, there's another aspect which we didn't talk about, like the part that determines these arrows. I think I'm a little confused about where they go. How do we understand the MLP from the perspective of these equations? So now we have an understanding of the attention heads.
So we need to get from this the red figure.
Yeah.
Right?
Is it true that the red figure is what you see before after the attention? What do you actually? What is literally the thing you're plotting in that plot?
Here's another name for hidden or latent middle. It's more, it's not a property of a layer so much to be hidden as a property of a position of a layer. Like imagine a neural network that has 3 layers. By convention, the 0th layer is the input x. Like, you know, applying a function 0 times its identity, so sure. Then the first layer will be the first matrix that's actually multiplied by x. then activation. Whether an activation is counted as a separate layer or not depends on like what you're talking about. If it's more convenient to consider it as like one functional unit or not. Technically, by compositionality, you can consider several layers to form their own meta layer, which is a very common principle, but people will then call that a block. A hidden layer or a latent layer, or thinking if there are any other names for these. They're just like the matrix is the middle. Yeah. Yes.
It's very
So
cool.
the middle.
That predicts
Yeah, because like the first one tends to have a fairly direct interpretation of how it acts on the input, and the very last one tends to have some interpretation of because of how it's supposed to be related to the output. But the stuff in the middle can be like anything in the worst case. So yeah. But it's also where all of its power comes from, this dream semantic space, the dream time.
These are empirical.
N in and N out, where N should really be D for dimension. This is why variable names are important, and why I called mine in underscore dim, and I'll call the other one out underscore dim.
Like in general, I expect them to be something like this. Like they kind of
What happens? Right? So this point goes to this point, and that point goes to that.
yeah. I think so. I don't know how much I'm doing there.
So in this particular case, there's no folding or anything, right? It's just squeezing.
Yeah, and I think like actually I think this point should go like this. So they're like those points are pushed on this axis. They're pushed on this axis. Then you have those points being pushed on this axis.
Yeah. Okay.
So and there'll be like a function which will like I think it will be something like convex function as you move along this axis. You go down. Oh no, it will be like maybe it will even be a linear function. That'd be interesting. It's like the displacement will just like shrink, and then it will flip and it will like be in that direction. I should have like just need to check what it looks like.
Okay. There are a few parts of the story that I think are a little shaky. So
Yes, I think so, because if you each of these neurons as they're set up is a list of weights of dimension I for n, and can act on, it doesn't act on a scalar, it acts on a vector returning a scalar. Yeah, each of these rows of weight, like a row of weights for a neuron, can act independently and will return some vector, and then the output will be stacked together into a matrix.
yeah, now I am wondering. In that case, that's less symmetric. How things look, but actually might be able to tell us a lot about how to interpret these. I guess there's still a bunch of questions I have about like.
Yes.
Yeah, I think I agree with you. I'm trying to learn this.
Yeah, and since you'd have output many neurons, your final list would be of shape like output by one, or
I don't have to
output.
like have a 500% completeness story necessarily.
Which makes sense since
Like just explaining the story.
it'll be some list. No, it'll be a list of a shape of out dimension, which I don't know. A shape n out as he's named it.
Yeah.
Like imagine a matrix with out many rows, or n out many rows, and n in many columns, times a vector of n in. Yeah, giving you n out.
Updating structure. It's geometric.
Yeah.
Structure, and that's represented in the transformer. And how does that cash out in terms of intermediate representations inside of the transformer? Okay. Right, because like what do we expect? Like how does the transformer actually build it up? Right? The representations before the full thing. Okay. For I have a story where I can predict attention items that, structures that I can also predict in full.
Mm.
And it's not the belief state geometry, the optimal predictor, but it's on the path towards building them. You can find those representations in the transformer as well.
Okay.
I think everything just says it's true. Is that true? I mean, you gave me a predictive story
Yeah.
about the fractal structure, which is not the belief state geometry structure,
Yes.
in the middle of the transformer,
Yeah.
before the elopement. You also gave me a story, which I'm not 100% sure is true, but it sounds like you think it's true. That you can even predict, not in 100% of cases, but in many cases, the attention patterns themselves.
Yeah. And also, it seems to me you can predict when it's becoming like when transformer needs to go to a different solution, meaning like when 1 minus 3x goes below 0, you cannot just like follow this attention pattern.
Yeah, there's like a bifurcation. So, yeah.
Maybe just in more directions. So much.
Yeah.
Like let's imagine that instead of having the 3 of those, you
Yeah, and the process of tuning these weights and biases, which I'm just going to call weights, because the biases are really just weights that are like organized a bit differently at this point, at the level of abstraction we're on. Yeah, like you have some set of weights, which initially is total guessing. Like the more sophisticated approaches are not that much better than total guessing, and so this works perfectly fine. And then through lots of data and little tweaks from each point, yeah, you'll get better weights that hopefully contain the answer to everything.
Yeah. I'm not 100% sure.
And it seems to work fine.
You show a bunch of these graphs fractals. Yeah. You say, what does it look like before the right after attention? Right after the NLP. You show that, yeah. So that means more fractals. Here. And in particular, you're going to point at like this thing that happens after the attention is highly structured, but it is actually not the structure of the belief state geometry. It's something else. And yeah, now I'm going to tell you a story that explains that. And correct me if I'm wrong, there was some story about how that intermediate.
Here, pause it for a sec.
It's probably better.
So yeah, he's just computing the squared difference, and then his next step will most likely be to take its mean, since he wants one number and he has 4, to get mean squared error.
It's quite
And that's like the default loss function for anything that's supposed to be continuous output. For discrete output, some sort of cross entropy or KL divergence is by far the most common. That's pretty much it. There's more sophisticated stuff, but these are really the big two. All
Yeah, I think that's interesting. This is like
right.
this structure of like T is only like delayed, only response to latents.
yes.
Only.
Yeah.
It's the Markov structure of the hidden states.
And
Even though
actually, these sequences give a good way of illustrating like what GPT and self-supervised learning does. Imagine you don't have the Y's, but you have the X's. Then, well, you can create Y's out of thin air by, well, lots of natural transformations on lists. Like, for example, use all but the last element to predict the last element, or the first element, or the third, or whatever. But, last is an obvious one, aka next token prediction, which is all that GPT does, and this is remarkably successful. It's self-supervised because you don't necessarily have an output, but you're creating one, basically building it out of your input. Sky's the limit there with your creativity, because there's so much implicit information in like basically any real object.
It's just so, yeah.
No, this
All right.
symbols. No, this is
Yeah, it's the special properties of the two norm and its inner product relation. It also has the great advantage it can be calculated very efficiently as like to find the norm squared of something as a vector is just it times its transpose, which is super fast, very optimized. No one takes the square root though. Yeah.
It seems to me that like
okay, sorry.
compute those, and then you still do the thing of the symbol.
But how do you compute those?
Something called I think it's
It needs to be somewhere here. Do you have equations for R?
I think this is they relate to the standard state from the steady state that we're observing. So like imagine that you start with some whatever you start with whatever state, you take one with like whatever symbol, and that should be the direction that you get.
I have questions. Do these arrows depend on alpha?
Yes and no. It only in the sense of like after the like the negative. After the alpha plus 1/3, they will like flip. Other than that, they might the scale of those arrows might. Yeah, it's actually. I don't care about the scale because they all should like. But I can imagine them being.
Okay, let's see.
Can you set the resolution of the video higher? I think it'll make his text sharper. The little settings wheel.
The key that's missing is like a explicit relationship between these two matrices and these arrows. If we have
Oh, that's way better.
So for better or worse, there's an enormous amount of symmetry here.
Yeah.
Which is why I was a little bit hopeful that if we go to a non-symmetric case, maybe the non-symmetries would bring
Oh, this is gonna be.
some things that overlap, some things that don't. It would be obvious where things are. But I'm not sure. Yeah, it's not obvious to me what exactly the right way to go about it is. So
The way I think about this stuff, it's like it does seem important over. It's like if there's a generic way to do like this update, like part of the function, not supposed to be recursive, it's still accessible to
yeah.
That's very interesting.
Yeah.
It's so each many also.
Yeah. Yes. What do you expect in the case where you have a different number of hidden states than emissions? So the number of arrows has to do with the number of emissions, right?
I imagine that.
Yeah. Sometimes you do control the inputs, but typically it's for interpretability reasons, like creating an image or input, like a sentence that will maximally activate a neuron. But there you're deliberately flipping the relationship back. Like ML's big conceit that's so successful is to first go work in configuration space by just restricting attention basically to the weights, or at least all the complexity shoved into them and into the data gathering.
HTML.
Yeah.
This guy.
Okay.
Like, what I think is like you still have those two arrows, but like given symbol A, you combine those two arrows according to this. Right?
Well, okay, so you think it's actually the arrows are according to the states.
Yes, and if you have more emissions, you will just combine those arrows to get a new arrow.
You wrote it.
Okay,
That you want.
I mean, you can certainly instantiate a small HMM.
X1 would be a whole row.
I think like
Like you said X1 through N. Like that matrix he provides as X's, that's what, like a 3x3, 3x4, 4x3? 4x3, 4 rows, 3 columns. That is 4 separate inputs, 4 samples.
in the future, right?
I want to try to make sure,
Yeah.
try to make very explicit the question you're trying to ask.
As it's set up, this is a map from like a 3-dimensional space to a 1-dimensional one.
The attention head naturally. You're in a current position.
Yeah.
Try to update yourself as by looking at the past tokens. And we conceive of that as essentially a set of weights.
Like in the case that there's just 3 of them.
These tokens. And you're saying
Oh, yeah.
actually,
This is
fundamentally what is the thing that determines those weights?
this is basically the problem of generalization and overfitting. Overfitting is well overspecializing, like that would imply where there are many possible functions that could fit that one data point, as you know from like the contravariance of restriction, like more functions defined on smaller region. And basically it's one of those problems that's solved in practice by giving it lots and lots of data where it seems to focus on functions that people care about.
Yes,
Because like either it works everywhere,
yeah,
and from any page,
yes, yes.
then you come to like maybe you also come to like representations when like you see how this is getting sparse. Okay, so this will be 0.
Okay, let me say it in a different way. The point you're bringing up, which I think is a very deep point, is you're like, you comic people told me the Souls Agent updating story. Very nice. It's recursive. Transformers are recursive. Just aren't. Which is true. There's kind of like what the fuck is going on there? If that's the case, like, how is it ever the case that you can see anything like the wave state geometry? And can we connect a recursive equation to the non-recursive form of the transform? So to kind of understand, it's not just why we happen to see it in the case of these S3 things, but kind of more generally, like, what are the limitations? Do we expect to see it? What do we expect to see it?
I don't know if you noticed, but the values of the gradients given are many of quite small magnitude, like 0.0001, 001. Some are closer to like 0.01, pretty small.
With some crazy attention. Then it's not impossible to input.
Yeah.
Like it's maybe
Yeah. I,
Mhm. All right, hit it.
Thanks, Friday. Okay, but it does seem like we're not that far away from trying to connect more concretely this to that. We got a little closer to it,
yeah.
at the very least, right?
But like okay, but like this yeah. Not that I mean it's very hard to touch on difficult those things are.
Yeah.
And like I don't know how difficult it is like to go from this recursive form to the right. I mean I don't think like okay this is easy because like once you know this you have this nice decay pattern relatively information. So it's easy, right? Like you might as well already maps. like this would be very obvious.
Okay, what should that be?
If that would exist, I think it does. It's already being tested. It's just like I just like also when I thought like all the stuff like that. I kind of know the questions I want to ask. It's just like, look, you don't. That's it makes me easier for me. Like, look, you don't update going this way. You just like update from this. Like you add this information somehow.
Thoughts? Yeah, don't overthink any of this. Like in the case of a layer, though, there's one layer of recursion in the parameters where the parameters of a layer are the concatenation of the parameters of each of its neurons, where he just defined parameters for a neuron, and now it's going to be called basically in a for loop to get it for a whole layer. And then MLP's parameters is going to do yet that one more time, where it would be the number of parameters per layer across self-dot layers. Uh,
Conclusion like this,
Yeah.
this.
I think as it's set up, no, that it should just flatten it into 1D. So it'd be a concatenation of them. Oh yeah. Well, the values are all there, and they're represented as a list in memory anyway.
Like if you.
All right.
Let's say you just start with this and just so you go that.
He's gonna do that extend probably. Params dot extend neuron return params.
So if you see A, you multiply
Yeah.
every row.
Appending would have created that matrix. Extending adds them flat. Like appending adds whatever you have, even if it's a container type or a collection, like a single point. And so a bunch of lists appended to an empty list would create a list of lists or a matrix. Whereas extending would unwrap the list that you're trying to extend from and would feed the elements as items individually one at a time. So extending by a list of length 5 would add 5 more elements. In this case, extend is defined on iterators in general, but conceptually, yeah, it does the same thing. Mm-hmm. Yeah. Well, actually, we do. That's how it's done. The next step to make this faster is batching, which is basically coalescing things into matrices, like that parameters function right there. The way that it would actually be done is that it would not return a list like this because that's copying every single value, which is very expensive. Instead, it would return an iterator which itself returns pointers to a matrix somewhere in memory. So it'd be a list, or rather a stream of arrows, each of arrow representing an integer that represents a memory address with some size info, where you could find the tensor that represents these parameters, and then another memory address for it, all to avoid having to do these copies. Instead, you have this layer of indirection of searching through pointers. Does that make sense? Yeah, the biggest models are 11 orders of magnitude bigger. Or 10 orders of magnitude, yeah. Yeah, it'll be like p dot grad times an epsilon. Yeah, it is minus. Yeah, he's probably going to put a minus equals in a second.
Strings on alpha, just 0 to 1.
Yeah, this is a basic training loop if you pause it. No way. No one, no. Yeah, and I think he picked too big a number for too many steps because when he said oops, his values, I think his loss went up instead of down since, yeah, like this, I mean, just like the calculus suggests, if you can take an infinitesimal step size, then this would be guaranteed to find a minima eventually, and therefore a sufficiently small one. A big one, you have no guarantee at all in general. But you do want, like, it's a fine art of taking as big steps as possible without going off the rails. Because, like, the magic number, the most common learning rate, which I think is the cuz of Andre, is 3e negative 4. So 3 over 10,000. And oh yeah, that's very common. Yeah, there's a whole thing of cycling learning rates, etc. Relatable. Yeah, where you define it like a data loader or some kind of loader that basically will zip together the data x and y. The loss function is usually just given as a very simple function. So that part of the loop is usually just repeated in line instead of being abstracted. So you would still expect to see the y pred, although there wouldn't be a list comprehension because everything's vectorized. The loss would just be computed. The loss dot backward is exactly how it's done even now. And then this for loop, it's abstracted into what's called an optimizer, which like keeps track of parameter values and is responsible for updating them. And so you would, instead of doing that, do something like optimizer.step. Oh, and there's also, if you want to run this in a loop, uh, dot zero grad, which will zero out the gradient at each step of your loop. Otherwise, it will just keep accumulating and accumulating. But go back a bit. Yeah, go back a bit more. I think he just lucked out, like dumb luck. That's a ridiculously low loss value. He got 7e negative 9, which is almost zero. Back more before he gets the negative 9. Because I want to see more. Go. Even he was surprised. That's the kind of value try to interpolate logarithmically, like between 0.01 and zero point 0.1, picking like 0.05 because it's like kind of in the middle. You want something that's in the middle on the multiplicative scale. Like 0.03 or something. I don't know. Log of 10. Mm. Yeah, but by step 7, it's basically done. Yeah, people have worked on it. The issue with all these hyperparameter tunings is that parameters are all the weights, yet another name for them. Hyperparameters are parameters that are tuned by hand, but one man's hyperparameter is another man's parameter. Yeah, you can definitely automate them. Yeah. Yeah, you can totally automate it. That said, it's like a pretty important one, and like plugging it too closely into your training loop, especially at the beginning, might make it weirdly unstable. So be careful. You have more latitude when they're mostly converged. Because he didn't zero out the gradient. He didn't zero out the gradient. He also doesn't take the mean, but maybe that's on purpose. Maybe he just wants the sum of the squares. So every time he calls loss step backward. The third one.
Can I share something? Can you give me your favorite values of X and alpha?
To like X and
This is a perfect example. We're doing the conceptually right thing. Actually, made the performance worse, at least for his case. Nonetheless, it is more the right thing to do. Where when he didn't zero out the grad, aka a bug, his convergence was much faster. By step 7, he was at E negative 5, and now at step 7, he's at E negative 2. So it's what, 1,000 times better? That said, like, if you, like, because gradient descent's pretty powerful, you can have all sorts of bugs like this, sign errors, etc. And debugging them is quite difficult because your model will still work, but maybe slower than it could have. So you gotta be careful. For the gradient?
Okay.
There's no obvious candidate for what else to multiply by, and a lot of this is hinging on the fact that he only has, what, 4 data points. Like, yeah, if you had a billion data points, you would want to zero the grad.
T-O. Okay. Taking the eigenvector associated. So, okay. I'm taking so now I have 3 eigenvectors. For each of those, I'm taking the eigenvectors that is associated with the highest eigenvalue. So one possibility is that these are where 3 are. Yeah. Now, let me know if this is true. So one,
I think there will be sorry. Oh well. For this one. Oh wait. Can you just project them on something?
You can go even faster.
Let's do it. So you did something.
Make our boy move his mouth. Make our boy move his mouth fast.
Yeah, I just want to see if they will.
actually this. Yeah, so one thing I can do. Two values.
Well, then you would
Two.
your representation just collapses to the form ax plus b, some affine map with all the limitations thereof. Like, I mean, you're literally restricted to lines.
Just cause it got the
Point three, 1/3.
control.
So let's do 1/3 minus 2 1/3 plus 1.
Like this. Right, it's like how to explain it.
Here, pause. Fucking object orientation. What he's doing here, he's created, yeah, a class called module, which is aping PyTorch's NN neural network dot module, which defines like a functional unit, something that has a call method and parameters, although possibly empty. And then he defines two functions that anything that inherits from it, like on line 13, you get class neuron parentheses module. That means that you're defining a class called neuron, and in those parentheses, it would be a child class of everything within them. You could have module and then a comma separated list of, well, whatever you want. You could also have nothing at all, and then you can leave out the empty parentheses, which is what's more common, like what module is doing on line 4. And it gives default implementations on line 6 and 10 for zero grad parameters that just do it in like the obvious sort of way. Anything that's supposed to subclass module or be a child of it is assumed to have a dot parameters method. Certainly, since they provide the default implementation, which returns an empty list, which is really meant to be overridden. It's more that he wants to define a parameters function that child classes need to implement. But his default implementation is the limitation of Python. That default implementation is just wrong.
See more like some. I don't understand. When you assume a sum, the answer.
Yeah. That's more opposite. He's just writing out a bunch of arithmetic and making sure the gradients are what he expects them to be.
Multiplication. Yeah. You assume a different form.
Yeah.
Get literally the exact right answer.
And he's definitely stress testing the same entity because he wrote in the middle C equals C plus 1, which is definitely on purpose.
One second.
There should be something in this, right?
Here, pause.
It's like you have the answer. Just trying to figure out why.
Yeah, this is a good example of the flexibility of neural networks as a paradigm for solving problems, because the code is more or less the same, except the data being loaded is both different. In fact, totally different. It's not just random numbers, it's, I don't know what that's supposed to represent. But he just, like that MLP and the in 5 block model equals MLP of 2, 16, 16, 1. Where I think it's supposed to mean 2 layers with an input size of 16, an intermediate size of 16, and then an output of 1. So it'll return a single number starting with a 16 number. So it reduces 16 to 1. Then the loss, yeah, he's just creating data. He's also shuffling the data in case there are any correlations between neighboring indexes. But otherwise, it's basically the same thing. Like the losses, he's using the cross-entropy loss instead of mean squared error, but it's still computing a loss and then returning it. And then the thing below is his optimization loop, which he factored out.
Well, I
Alright.
won't know until we figure out. Okay, let's think. I mean, every time you see a system, it's like you're moving towards the state in the ATM that most likely exists. Right?
I mean, look, can we construct with HMI? Yeah. But this, yeah, you can construct with HMI. Keep on circle. Like, you see here, you see
Here you can pause because that's not too hard to explain. Typically, regularization of some kind is essentially trying to control the norm of the gradients and the weights to prevent the weights from growing like too big by absolute magnitude. Because you imagine a scenario where the weights by absolute value are very large, all of them, but somehow when applied to an input through all the sums and products, they basically cancel out to give something reasonable-ish. But it will be inherently super unstable because you have these big jumps in magnitude. And if you gave input that wasn't in the data set or not close to anything in the data set, you might just get like total garbage, which doesn't generalize well. If you like trying to fit 2 points with a polynomial that is like degree 16, it's overkill. So you'd penalize it. Actually, that's a good example of regularization. Say you restricted your output function to be a polynomial. One regularization could be on like the coefficient of the highest degree or the highest degree itself, something like that, trying to push it lower.
You have a very good intuitive story of observers, but we don't have a formal system.
See what you're saying right there? You were saying, well, changing the learning rate. Here he's doing it by causing it to exponentially decay.
doing something on right. The first and like the first one was one, so like so it's in one with probably right? Like this like then you see before that give it to how this work. And then say so then it's like probably something like over to let's see. And then you but like the important thing is like this is then the sequence you're done. You know what I mean? Like it's so like social this seems to be the same universal. You reverse that intersection. Yeah, it's like a mixed situation of like forward and backward.
This story you just told seems generalizable to me.
See, and he is not at all above just like Googling it and like looking up on a forum. No one's above it.
Crazy.
see. You can play with the arrows.
Whoa. What does it mean? Does it then converge to this other thing? Is it like the
It's truly ugly.
it like looks like it's gonna converge and then it decides something else that like it's like a phase transition.
Yeah, there's like a there's two phases.
That's true. Why is it in there? It's even weird. Anyway, that's funny. Sigmoid is in there too, which doesn't belong.
Looks weird because it seems like the triangles just collapse to themselves and like they come up the other way. And this is like when you start updating and this kind of stuff becomes affected. So instead of like just like going smaller, smaller, and you're actually going smaller, you just change signs also. And this like space transition.
That's cool.
This is the one that's like this is like the opposite of GPT.
Production library. Yeah, production grade library.
This is the story. This one, yeah, the story. So you can predict intermediate frames in the transformer. Believes in geometry pattern.
Uh-huh.
Our story. You can
Not the higher.
As they say, something make a prediction. Not sure that it's true. But exactly how I read this in the equations, I believe something. So you get like this
How did you
intermediate.
come up with that?
It's just like incorrectly I observed what's happening and extrapolated and like but like there's just I know very well how it works for tests.
Well, for any of this three.
Yeah. And for like this specific HBAC, I have like a hunch that it should like work always in some form. And it sounds in some cases like the transform models will be able to implement that. In that cases they want one. So they will probably find some more solutions to do it. Yeah. But hard.
Yeah, the suggestion. The suggestion is to start making some panels that tell the story. It is actually possible to tell the story. Like, I have a complete poster already with this stuff.
Okay.
There is this open question. We actually connected to the equations. Should be great to figure out. But that's also not necessary. It is all very cool stuff. It is. Feels that way.
All right, what do you have?
Like there's a bunch of cool things to show.
I will.
Okay,
The next thing to see maybe tomorrow, which will go straight into MechInterp, would be like 3 blue 1 browns videos. You should probably watch if you have. Okay, I already added to your stack. What essence of like neural networks? There's 5 parts. Like I think the first one's like, but what is a neural network really? And then there are more recent videos. Not that one, but what is that one? Yeah, but yeah. Yeah, like everything up to, but what is a GPT? Not inclusive. And then we would watch, but what is a GPT? Because now that you've seen a neural network, now you can see some visualizations, and then we can go on to transformers. I also recommend trying to write out Karpathy's micrograd from scratch. Just create a data set by just using numpy.random to make up data points and test it.
True intermediate representation before the after the attention.
Oh, but
Actually, it didn't even like
all right, then I'll see you later.
the rest of it. We're just looking at it.
All right.
So it's like